Welcome PCS members and friends to our today's IBS PCS seminar. It is a great pleasure to have with us today Professor Yong-Baek Kim from University of Toronto. And I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Yeah, okay. I hope everyone can hear me, and welcome everyone. This is our first on-site in-person seminar since quite a while. I forgot when it was the last time. It's a great pleasure to have Professor Yong-Baek Kim with us today. Yong-Baek Kim comes from the University of Toronto. He did his Master of Science at Post-Tech in Korea, and then he moved to the States where he did his PhD in 1995 at MIT. Then he started to move around the United States, mainly first Bell Labs, Rutgers, Pennsylvania State University, Ohio State University already as assistant professors, and then he moved to Canada, further north, University of Toronto, where he is since, where he is now a full professor and director of the Center for Quantum Materials. Yong-Baek Kim has a number of honors and awards, and I will not read all of them, but just mention a few. He has a Brockhouse Medal from the Canadian Association of Physicists, and since very recently he is a Simon Fellow for Theoretical Physics and a Guggenheim Fellow, or a holder of a Guggenheim Fellowship. I don't know how to correctly say that. He is a well-recognized specialist in condensed matter physics and has more than 250 publications. And moreover, we have a plan to run an advanced study group with Yong-Baek Kim as the convener for the next 2 years at our center. So I hope we will see you quite often and frequently at our center. The advanced study group will work on or research on entanglement and dynamics in quantum matter. And today we will listen to your talk on realizations of fractonic quantum phases in frustrated magnets. So let's welcome our speaker.
Thank you very much. I'll try to speak with a mask, and if it doesn't, it becomes unclear, then I'll take it off. So we'll see how it goes. I haven't given an in-person talk for a very long time, so I think this is a new experience for all of us. So we'll see. Great. So today's topic is what we call fracton quantum phases. And you will see that this is a very strange phase of matter. And there have been some exactly solvable lattice models for these phases, but it was never really identified in real material. So the purpose of this work was to see whether we could realize these exotic phases in what we call a frustrated magnet, basically interacting spin system with some, on some geometrically frustrated lattices. So I will tell you what they are. I'm moving. That's stuck. Strange. It got stuck somehow. I should stop sharing. Yeah. But then I'm not sharing, so I think I should see. Well, how do I get out of this screen? Zoom? Okay. It's better not to do the full screen, so I think I can just do that. Yeah, this is better. Okay. Yeah, so then it works. Yeah, okay, great. Okay, so I'm going to give you a very brief introduction to topological phases and this fracton. This is kind of relatively new concept. So in the last like 10 years or so, we have seen like expanding landscape of topological phase matter. So largely there are two kinds of topological phases we know of. So one of them is famously called symmetric protected topological phases. The most famous example is a one-dimensional antiferromagnetic spin one chain. So you have a one-dimensional spin system, and the spin magnitude is one, and they are interacting with each other antiferromagnetically. So the nearby spin wants to be anti-aligned. So it's known that such a ground state of such a system, in the bulk, there is an excitation gap. There's a gap phase of matter. But if you have an open boundary condition, then you can generate a spin half boundary state. So it's kind of strange, right? Because the bulk, the system is actually interacting spin one system. The bulk is gap, but at the boundary, if you have an open boundary condition, you generate a spin half object. So you have a fractionalized spin excitation at the boundary. And it's known that such a phase exists. We know, you can actually show almost rigorously. But it turns out that in order to have phase like this, certain symmetry has to be intact. For example, for this famous one-dimensional spin one chain, there should be a spin rotational symmetry, and there should be a Talley-Russell symmetry, and things like that. So if you remove those symmetry, though, the interesting topological property is basically gone. So that's why it's called symmetric protected topological phases. And now there are many more classes of such a topological phases of matter. But mostly, people talk about a band topology, right? So non-interacting particle, looking at the band structure, and depending on your symmetry, you can get like topological insulators, topological superconductors, and topological semi-metal. But the central theme is basically the same. For example, the bulk of the system may be gap, but if you go to the boundary, then you have some interesting gapless boundary state. Again, if you remove the symmetry, then they will be all gone, right? So that's basically the idea. But we have also known something called the long-range integral state. These are actually older topological phase of matter, things like a fractional quantum Hall state and quantum spin liquid and things like that. And the point is that these phases don't rely on the symmetries. It has nothing to do with the symmetries. So even if you don't have any specific symmetries, these phases are stable, basically. And so now the new kind of phases were sort of identified, and these phases are called fracton phases. And in this case, not just topological properties of these states are important, but also the geometry of the actual lattice is also important, it turns out. And these phases were initially proposed by quantum information theorists, actually. And they basically solved these phases as a possible platform for quantum error correcting code. And then some high energy theories jump into this field, and they found that to describe phases like this, if you go to a continuum limit, you need some special kind of quantum field theory. So it turns out that in this kind of quantum field theory, not just the long distance properties, but you also have to worry about what happens at the short distance scale. So you cannot just think about a coarse-grained long wavelength theory. That's normally what we do in quantum field theory, but you cannot do that for such a system because the property of this phase explicitly depends on the geometry of the lattice. So I'll explain that to you. I explain later why that's the case. And also it's related to the idea of a quantum glass. It turns out that there are a lot of degenerate ground state in this kind of state, and because of this, there's some relaxation of one ground state to the other becomes very, very slow. So there's some connection to quantum glassiness. Okay, So just to tell you a little bit more about this long range entangled state, just in case that you don't know about this. So the famous example is a quantum spectrum. So this is some kind of long range quantum entangled topological phase. So what do you mean by this, right? So what do you mean by long range quantum entangled state? So operationally, what that means is that if you start from such a quantum state, and then by doing some sort of a unitary transformation, I cannot write this state as a product state of short range entangled block. So here's an idea, illustration of this idea. So one of the famous examples is what people call resonating valence bond state. I'm sure that some of you heard about this. So think about some spin system on the lattice. In this case, I'm showing you the square lattice. And spins are interacting antiferromagnetically. So naturally, they want to make a spin singlet out of it. So you place those spin singlet configuration on the lattice in some pattern, right? But then there can be many different kinds of covering of the lattice by those diamonds, right? Then you think about a linear superposition of that. So that's like a Mickey Mouse version of the quantum spin. So obviously, by construction, the ground state is spin singlet. But if you think about like looking at this state in time domain, you will see that these diamonds are basically fluctuating between different diamond configurations. Okay, so now a different way to look at this waveform. So this is a famous representation, but there's a less known way to think about this. So imagine that I start from a reference state like this, that I superimpose this configuration on top of that, then you can generate what people call a transition graph. So what you find is that it basically consists of a lot of loop configuration. You can make a loop. So if you pick a reference state, then this resonating valence bond state, or some people call it diamond liquid, you can think of that as a sum over loop configuration. If you do a one-to-one mapping to this transition graphs. So this idea was put forward some time ago. So the point is that if you have such a complex, if you like, loop gas state or a string gas state, then one can show that there's no local unitary transformation I can apply to such a state, such that it becomes something very simple like this. So here, I'm just showing a simple example here. These two spins are making a spin singlet. So this block is obviously entangled. These two spins state are entangled, but it's a short range entangled. It's entangled only between two nearby sites. But then you make a direct product of that. So this is the example of product state of short range entangled blocks. The point is that you cannot go from here to here by making a local unitary transformation. So in that sense, this kind of state is long range entangled.
Can you go one slide back?
Yeah.
I somehow missed the point how you get to these loops.
Yeah, so you take this, I think I need a better PowerPoint presentation. You take this guy as a reference state. You take this one, then do the linear superposition. Okay. Not the linear superposition. You place this guy directly on top of that. So you place this guy here, here, and this one here. So then you make a loop like this. And that's this loop. So the point is that for every other configuration I can generate, if I use this as a reference state, you will generate some loop, different kind of loop configuration. So in that sense, summing over all diamond configuration like this corresponds to summing over loop configuration like that.
And where's the long rangeness coming in?
The long range is, it's hard to explain here, but the point is that all these loops are basically the size of the loop can be arbitrary. It can be a very large loop or very small loop. Okay. So it's very hard to disentangle this to a short range block like that. So that's basically the idea.
And do you have any constraints on the unitaries which you apply?
No, this is,
You say
basically
any unitary.
any unitary. Yeah. So in that sense, it's different from symmetric protected topological.
And what means local unitaries then here? No local unitaries.
Oh, this means that there's no local unitary transformation from here to here.
And what means a local unitary transformation?
You apply a unitary transformation locally at this place, that the other place.
Okay.
So
So some
this
kind of
means that-
commuting local.
Yeah.
That's what you mean. Right?
Yeah. That can be arranged, but even if I start with the even by even lattice, you cannot rewrite this state like that. So that's basically. That's true, but if you go to a thermodynamic limit, you can argue whether 10 to the 23 is even number, odd number. I mean, it doesn't really make any difference.
Right. Yeah. Thanks. Yeah.
Right. Okay. So one interesting property of such a state is that there's some kind of interesting ground state degeneracy. So, for example, if you place a quantum state like this on a sphere or a genus 1 torus or genus 2 manifold like this, then you can show that the number of degenerate ground state changes. Like here, number of degenerate ground state there will be just one ground state. For torus, there may be 2 degenerate grounds. And here, maybe you may have 6 degenerate grounds, something like that. So it changes depending on the manifold. This is very strange. This is the reason why these phases are called topological phase matter. Yeah. So obviously, the trivial ground state of interacting system, like say you take a piece of copper, you wrap it around the sphere or torus. Obviously, the ground state will be unique. So for ordinary phase matter, this doesn't happen. So in that sense, this is a rather exotic phase matter. Another interesting property is that here the ground state is like some of closed loops, if you like. But if you open up the loop and make an open string like this, then the end point of such an object is basically one of quasi particle, and they generally are described by the anionic particle in the sense that depending on the types of excitations, their braiding properties. In 2 dimensions, in particular, the braiding properties basically follow this anionic statistics. Okay, so these are the sort of ideas about long-range entangled state. So this is a rather old idea. This, if you like, that was a description of old topological phase matter. This one is new. Now, what happens is that when you create a quasi-particle in the fractonic order phases, what actually happens is that quasi-particles actually have a restricted mobility. For example, there are particles that can only move in only in one direction. The system is 3-dimensional. Ground state is a 3-dimensional state. But if you create a quasi-particle, some quasi-particle can only move along only one direction. They cannot make a loop, right? They cannot take a corner, make a turn. Then there are also quasi-particles called fractons, and those guys show up at the corner of some kind of membrane-like object like this. So these are the excitation, basically, out of the membrane-like manifold.
That's real space.
Yeah, these are all real space. Yeah, and in some models, those excitations appear at the corners of the fractal object. So I think that the name fracton comes from this figure. Basically, those excitations that exist at the corners of the fractal structure. So you see what actually happens is that you can expand this membrane. Then these corner excitations, basically, they become farther and farther apart, right? And the same is true here. I can expand this fractal structure, make it bigger and bigger, but you cannot get rid of all this corner state. And on top of that, you cannot excite a separate excitation like this. In this case, you always have to create these 4 excitations at the same time. The same is true here. You have to create those 4 excitations always at the same time. You cannot just create 1 excitation each. So that's the constraint for the quasi-particle excitation. So there are exactly solvable, what people call commuting projector model. So there are many of them, but the most famous one.
There's another end of the cable. Maybe the problem is with the other.
It's possible, yeah. This one.
There's another end of the cable.
Right. Okay. Hopefully it's better. Okay. You can hear me, right? Okay. Great. So there are exactly solvable what people call commuting projector models, and these are the models that some quantum information people proposed, and some condensed matter people, especially this fellow Jung-Won Ha, proposed those models. Actually, he was the first person who identified such a very exotic state in 2011. So the model is very simple, actually. So think about a cubic lattice, and the Hamiltonian consists of 2 kinds of terms. So these are the so-called vertex term. This is the cube term. So you see that in 3-dimensional cubic lattice, we have these 6 directions like this. Then you take 2 axes to define a single plane. Then for each bone direction, so with respect to this each vertex, there are 6 bone directions, but you just take 2, and then you place sigma z Pauli operators. That you just make a product of them. So it's like a sigma z, sigma z, sigma z, product of 4 Pauli operators for each cross like this. And then you do that for the different plane. So that's what I mean by x, y, z. Okay. So the sigma. So the product of 4 sigma z here, product of 4 sigma z here, product of 4 sigma z here. Those are 3 terms. And this is a complex term. So here we think about a cube. Then you place sigma x operators at the edge of this cube. So there are 12, right? So it's like a product of 12 sigma x operators. It's a horrible model. Okay. So horrible model, but the reason why it's useful is because this model is exactly solvable. And this model, this A term and B term, they commute each other. That's why it's called the commuting projector model, right? And the point is that with all this minus sign, the ground state is characterized by the following condition. All the vertex term, is +1, cube term is +1. Then that basically gives the ground state. It's pretty simple. Okay. So yeah. But what's interesting is that the number of quantum spin configuration that satisfy this is not just 1. There are many, many states that can satisfy this ground state condition. So in fact, if you count the degenerate ground state that satisfy all these conditions, then it turns out the ground state degeneracy actually depends on the geometry of the lattice. And more explicitly, the model that I showed you is called the XQ model. I mean, the reason why it's called XQ model is because there are X, then Q. So let's go, it's called XQ model. But if you count the number of degenerate ground state, then it looks like this. It's exponentially large, but it's not scaled with the volume. It's actually scaled with the perimeter of the lattice. It's very strange. But what is interesting is that
What's the perimeter of
so definition is just Lx plus Ly plus Lz. So I'm talking about the final lattice. There's a all edges, all edges. So it's exponentially large, but it depends on the basically the sum of these three lengths directions, right? So that's the conclusion. So this is exact result. So this is very strange. Remember that for the old, more traditional topological phases of matter, the degeneracy of the ground state depends on the manifold, but it doesn't depend on the lattice size. It doesn't matter, right? How large the lattice size is, it's always the same. But here it's changing, right? So this is very strange. So let me see, So that was the beginning of this fractonic story. So now there are a lot of development around this phase of matter. There are like people try to write down some kind of continuum quantum field theory for this. This is kind of a very difficult task because the ground state just depends on the lattice size. So you cannot just write down a long wavelength quantum field theory. So you have to do a lot of modification of the QFT. So that has been done by many people. And there's also an interesting relation to elasticity theory. So it turns out that in some elasticity theory, it's basically the deformable continuous medium kind of thing. Those strange excitation basically corresponds to dislocations and disclinations. So there's some connections, especially in 2 dimensions. Then there's the connection to what we call a rank 2 tensor gauge theory. So this is something that I like to explain today. So it's a generalization of the usual electromagnetism. So there's some connection to do to this kind of theory. So this leads me to talk about this higher rank gauge theory. It turns out this higher rank gauge theory is related to this fractonic quantum matter. So I'm going to explain what they are. So just think about an ordinary electromagnetism that we learn in the textbook. So that's like a rank 1 Yuan gauge theory. Rank 1 means that my electric field is just a vector. Okay, so that's what we are familiar with. So there's a Gauss law, and this is a Poisson's equation, right? When there's a free charge, right? Everybody knows that. And there's a corresponding gauge transformation. I'm just only showing the electric field, but you can do the same for magnetic field. So what do you mean by rank 2 theory? It's just pretty simple. You just take an electric field. Now it's a 2-index tensor. So think about a matrix, 2-index tensor. Then there are 2 different ways to think about a Gauss law constraint. So if you contract all the indices like that, then the corresponding Poisson's equation looks like this. So in this case, the charge you can create is a scalar charge. And this is the corresponding gauge transformation. You can do something else. You can contract only one indices. Then when you write down a Poisson's equation, now your charge actually becomes a vector. It's a vectorial charge. So you can write down either scalar charge rank 2 Yuan gauge theory or vector charge Yuan gauge theory. So at this level, this is very formal, right? So far, there's no connection to fractons that I talked about. So now, what's the connection? So point is that if you think about rank 2 Yuan gauge theory like this, for example, and one can show that this basically gives us 2 kinds of constraints. So remember that in the usual case, the Gauss law means charge conservation. Basically, there's no free charge, right? So the total charge is 0. Charge is conserved. If you have a constraint like this, one can show that what that means is that there's actually another constraint. So not just the total charge, but all the dipole moment is conserved. Dipole has to be conserved. So general charge configuration is something like quadrupolar charge configuration. So you imagine that you start from something like this, plus, minus, minus, plus. When you try to deform the charge configuration, you can do this. Then you notice that by deforming this way, you conserve the charge, you also conserve the dipole moment. But you have to move the charges in such a way that these two conservation laws are satisfied at the same time, right? So that gives you some constraint on the motion of the charges, essentially. So you can do the same for the vector charge. So in this case, it turns out that, of course, the vector charge has to be conserved. But something like, in this case, pseudo angular momentum kind of things also has to be conserved, in the sense that if you think about charge as some kind of momentum density, then this is like angular momentum density, right? So yeah, so these two conservation laws has to be satisfied. By looking at this, you immediately realize that if I try to move my charges in this case, because the cross product has to be 0, right? The charge's motion is restricted to the direction along the charge vector direction. You cannot move perpendicular direction, because if you do that, then you break this conservation. So generally, the main message here is that if you look at the rank 2 Yuan gauge theory, then motion of charges is restricted. So that shares the same property as the fractal phases I talked about. Okay, so there's some close connection between this rank 2 theories and the fractal phase matter that I talked about. Okay, so that was the long introduction. But so now my main purpose was like, can you construct a realistic model for this kind of thing? Yeah.
Components, what are they?
Yeah, so this like a you can say X, Y, Z.
So what are these? Are these one charge? Let's say the X component can only be X direction, or what?
That's right. So X component can only move along X direction.
And the Y only in the Y direction.
That's right. That's right.
So you have 3 different or whatever.
That's right. That's right. That's right. Yeah. Yeah. So far, everything is just abstract. Okay. Okay. So what are the examples of this in condensed matter system, for example, right? So I'm gonna explain to you just in case you're not familiar with. There's something called the quantum spin ice, and we think of this as an example of emergent Yuan gauge theory. This is the ranked 1 gauge theory in the condensed matter system, and so I'm going to review this very quickly. Then there was a interesting realistic spin model, but classical model for the rank 2 Yuan gauge theory on the what people call a pyrochlore lattice. And then I moved to the quantum model. That's actually the main thing that I wanted to talk about. Okay, so I'm going to review this. Okay, so here is the idea. So I'm going to start with this famous example of classical spin ice. So you have a lattice. This is called pyrochlore lattice. So corner sharing tetrahedron, and lattice like this is abundant in nature. This is one of the most commonly available lattice. Okay, so now you take a spin sitting at the corners of the tetrahedron, and you define a tetrahedron spin. It's a classical model, so you won't have Ising interaction, the G component. You sum the Ising spin on the 4 vertices of the tetrahedron. You define a cluster spin like this. So one can show that if you start from an Ising model like that, then you can rewrite your model using this cluster spin. You just have to simply scale them and do the sum over all tetrahedron. If you do this, then every side is counted twice. So in order to correct the mistake, I need a factor half. And up to constant, this is the same. Okay. Now what it means is that now you want to minimize the energy classically. It's clear that the solution is very simple. I have to have basically minimum value for cluster spin, and that's 0. So that basically corresponds to the famous ice rule. We have a 2 out, 2 in spin configuration.
Why ice?
Oh, because if you look at the water ice, then the position of the proton is precisely described by this orientation. So you can have a 1-to-1 mapping from water ice to the spin ice. That's the name. That's the name, right? That's the reason why it's called the spin ice. Okay. So, the point is that there are many possible 2 into our configuration. Actually, even for the single tetrahedron, there are like 12 different configurations. So if you place on the lattice, you can imagine that there's an exponentially large number of spin configuration that satisfy this constraint for every tetrahedron. So it's a very degenerate spin configuration. Now, how can you make it quantum? So you just have to add transverse term like this. So now these are quantum mechanical spin operators, so they don't commute anymore. So now you start from classical spin state. You turn on this quantum fluctuation, then see what happens. So it turns out that if the Eisen component, if J perp, this ferromagnetic XY spin interaction is large, and obviously you will go into XY ferromagnet. But when you turn on a small J perp, small transverse coupling in addition to the Eisen interaction, then you can get into this famous quantum spin ice state. And I'm going to explain to you how you can get that. Okay, so to do this, you need some kind of mapping to electromagnetism. So that's what I'm going to explain. So now think about a classical system. So the original lattice is pyrochlore lattice. If you take the center of each tetrahedron and connect them together, it becomes a diamond lattice. So diamond lattice is a bipartite lattice. So you can have A side and B side. There are two types of lattice site. Yeah, so you just connect the center of the pyrochlore lattice, just becomes a simple diamond lattice. In this case, so this, this is a picture of the diamond lattice. The spins are actually sitting at the bone center of the diamond lattice. So this is called dual diamond lattice. So the spins are sitting at the center of the center of the bond, connecting two sides on the diamond lattice. And you will see why I'm doing this. So the site on the pyrochlore lattice corresponds to the midpoint of the bond on the dual diamond lattice. So if you do this, then you can define what you call an oriented vector field. So depending on whether you're sitting at the A sub lattice or B sub lattice, you define a different sign for this. So you call this operator E instead of S chat because of the different sign structure for A and B sub lattices. The reason why you want to do that is because if you switch R and R prime direction, then this guy changes sign because of this definition. Okay, so that's the only thing I need. But advantage of doing this is that now you take some kind of lattice divergence of this field E, and it's like a summing over this link field, in oriented field. So basically you're summing over. You take one site, then you are summing over all the electric field amplitude. So E field amplitude for the nearest neighbor site. You sum them up. That's the lattice definition of divergence of E, and that's precisely the same as the magnitude of the cluster spin. You know that in the ground state, this has to be 0. So the 2-in 2-out configuration nicely maps to a Gauss law. So that's the way that we can map the classical ground state to electrostatics, if you like. Now, if you go to quantum model, it's slightly more complicated, but now you treat this quantum fluctuation part, J perp, as a perturbation. So then you do degenerate perturbation theory. Then if you do a degenerate perturbation theory, what actually happens is that you can do a third order perturbation theory by applying this. So on the lattice, what actually happens is that you flip the spin along this hexagonal loop in the 3-dimensional lattice. You just go around. So you start from some ground state configuration. You flip the spin, you go out of the ground state. You flip the spin, you are still outside the ground state. Flip the spin, you are still outside. You are still outside. But in the final spin flip, you go back to one of the degenerate ground state. So in that sense, it's a degenerate perturbation theory. Okay, is that clear? Okay. So if you do this, then you end up generating a ring exchange term around this hexagon. So this is the smallest loop on the pyrochlore lattice. So then this is the effective model, the ring exchange model. So now there is a nice mapping. So I told you that the G component, the spin can be mapped on some kind of electric field on the lattice. Now you can define a vector potential by defining vector potential A in terms of this the creation, so the raging operator of spin. So you know that Sz and S plus should satisfy certain commutation relation, and that translates into commutation relation between vector potential and electric field. You know, this is the usual commutation relation for the quantum electrodynamics, if you remember your textbook, right? So interesting, right? The spin commutation relation immediately become commutation relation for the vector potential and electric field. Now, if you look at this ring term, and you know, just rewrite all of your creation, raising lowering operator by this vector potential term. And if you rewrite it, then you generate this 2 times the cosine of curl of A. So this, whatever inside this here, those guys, this is the lattice definition of curl around the hexagon. So you generate this term. And if you remember that the electric field, actually the G component, the spin, we are talking about a spin half spin. So E square has to be always 1/4. So you can put some coefficient here, take the large U limit so that you make sure that electric field magnitude is constrained. Then you have this nice Hamiltonian. Here, notice that I have E square and the cosine curl of A. And the point is that if the ground state is near curl of A equals 0, then you can expand this cosine. Then you end up with E square plus B square Hamiltonian. That's precisely the Hamiltonian for the quantum electrodynamics. Okay. Now you get this. Then you can talk about elementary excitations of this. Obviously, there should be a photon, emergent photon out of this electric field and magnetic field. There's a linearly dispersing photon degree of freedom. Obviously, this is not a real photon, right? This is a collective excitations of the spin, but in every aspect, they behave like a photon. There are 2 polarization, and there's a linear dispersion, things like that. And on top of that, there's a electric monopole, or we call a spin-on. So that's nothing but you know, you start from a 2 in 2 out configuration, then you flip one of the spin, then you generate a 3 out 1 in state. That's basically my electric monopole. So the energy required to create such a state will be like, you know, order of J sub Z. Then there's a more exotic magnetic monopole excitation. These are the excitations that changes the flux around the bracket. So
Why approximate?
Huh?
For the
oh, because on the lattice, it's
okay.
something like sine k, right?
So that's long wave.
Yeah, the long area approximation. Okay, yeah, great. Okay, so now that's the ordinary rank 1 Yuan gauge theory. Okay, now can you get rank 2 theory? That's the question. Can you get rank 2 theory? So now story has become a little more complicated. So I'll show you how to do that. So in fact, we are going to talk about some models, spin model on the so-called breathing pyrochlore lattice. So generalization of the original pyrochlore lattice system. So here, the size of the tetrahedron is different for the A and B sublattices. And there are actually real material like this. So the spin exchange interactions on this lattice is different for A and B sublattices because, you know, the exchange path is different. So the magnitude exchange interaction is different for A and B. In fact, the exchange interaction for B tetrahedron like this is order of magnitude smaller than exchange interaction the A tetrahedron because, you know, the distance is much shorter. It's so much longer, so exchange interaction is much smaller. Okay, so, you know, there's a material like that. So now, you know, this is like, you know, the more 3-dimensional version of the pyrochlore lattice, is the breathing pyrochlore lattice. This yellow tetrahedron I would call B, tetrahedron. The green tetrahedron I would call A. Okay. Now, if I use this kind of picture, then I will confuse everybody, just too complicated. So I change that. So here's a picture. So the green dot, each dot is basically each tetrahedron. So each one of them is a tetrahedron. This yellow dot is the yellow tetrahedron. So each one of them makes a tetrahedron. So in fact, A and B sub-lattices, or the pyrochlore lattice, they make a FCC lattice respectively. So FCC lattice for A type, FCC lattice for B type. Great. So one can write down the symmetry allowed most generic spin model on such a lattice. So the same is true for A and B sub-lattices. You can just look at the A tetrahedron side. There's a Heisenberg interaction. This is what people call Jalochinsky-Moria. And this is the famous Kitaev interaction. It's a bond-dependent Ising interaction. And there's something called symmetric anisotropic exchange. So if you think about a Jalochinsky-Moria as an anti-symmetric part, this is a symmetric part of it. So this is all. This is the most general spin model one can write down if you're only concerned about nearest neighbor interaction. Okay. Okay. So we know that interactions on the B sub-lattices is much smaller than those on the A. And I'm going to assume that Heisenberg interaction dominates. So those are the largest interaction. All other anisotropic interactions are small. So that's what I'm going to assume. And that's very, very natural for this kind of material. Okay. Now, this model looks very complicated, right? So, and it doesn't really give us a lot of insight. So it turns out it's more useful to write down the same spin model using the normal coordinate or normal mode. We are just going to use the group theory. So think about a single tetrahedron like this. There are 4 sides. And think about a possible collective mode of 4 spin. Okay. Now we are going to classify those collective mode using elusive representation of the tetrahedron, the symmetry of the tetrahedron. There's a TD group. So these are the elusive, labels for elusive representation of TD. So you can write down, so and there are corresponding normal mode, M for the, so M is the normal mode coordinate. And you define it for A and B sub-lattices. And those coefficient is basically a mass, or the energy that's required to create that particular collective mode. More explicitly, it looks like this. It's a normal coordinate, right? So you just read off the character table. Look at the basis function. You know that combination of 4 spin like this. For example, for each irrap, these are the normal mode coordinate. So these are the the vectorial normal mode, and there are 3 components. Then notice that they just you can write it in terms of this coordinate. This is like writing a phonon normal mode out of the 4 atoms. It's basically the same thing. Okay. I just use the spin coordinate. Okay. So nothing fancy here. That's normally what we do when we analyze the phonon mode. Here's the spin collective mode. Okay. So again, I emphasize that if you do this, then because of the fact that each lattice site belongs to 1 A tetrahedron, 1 B tetrahedron, single site is shared by A and B sub lattices. So when you do this, there's overcounting. So that's why I need the factor half for both cases. But trust me that this model is exactly the same as the previous model. In fact, there's a one-to-one correspondence. All the mass scale can be written in terms of the original spin model. So we know precisely how that microscopic spin model is related to this collective coordinate. Okay, great. And we are going to assume that the Heisenberg interaction dominates. So there is larger than all other anisotropic interaction. If you do that, then you immediately realize that the heaviest mode, or the mode that requires the largest amount of energy, is the T1 plus mode. So here, the mass is the largest. So we are going to set those modes equal to 0. So we are going to throw away the high energy mode. We are just going to look at the low energy mode, usual procedure. But by the time you remove those mode, that makes the story interesting. So you remove this guy. By the time you remove this, for example, for the B side, this generates the constraint of the normal mode of the A tetrahedron. Why? Because every spin is connected to both B and A sublattices. So if you put constraint on this, then you immediately generate a constraint on A sublattice spin. Yeah, so that's the point. So to make the long story short, if you look at the constraint on the normal mode of the A tetrahedron, so remember that I removed those.
But you also want to put the same constraint on A.
That's right. So
what kind of mass?
yeah, so it turns out that removing those modes for the A does not affect the constraint coming from like removing this mode, the B sublattice side. So you have to make sure that everything is of course consistent. So you can show that that is the case. So for the A sublattice, you can just get rid of it. It doesn't really affect more. Okay, so the biggest effect is when you get rid of this mode on the B sublattice, you immediately generate some constraint on the A collective mode. Okay. So if you write it, so you notice that there are, I have to worry about these 4 nearby tetrahedron. So there's some constraint on the lattice scale, but then if you take a continuum limit of that constraint, it looks like this. This way it's not illuminating, but you can show that you can write it in terms of like kind of Gauss law.
But this constraint is approximate, right?
Yeah.
So also the degenerate, everything else is, so to say, an approximate.
That's right. So you have to. We are talking about the physics below the energy scale set by the mass for this stuff. So for example, if my temperature is larger than mass scale for this, then of course this physics doesn't apply, right? Basically, this mode is still alive. So I have to.
Sure. But what I mean is, I guess that there is still some small but non-zero parameter. I stress non-zero, even though it is very small, which let's say, I don't know, will not allow me to conclude that, say, some states are degenerate, exactly degenerate, but that that. So my question is, the fact that there is still a small but non-zero
You mean
because this is not exactly zero.
Yeah. Are you asking whether,
what is the consequence of that?
That's right. So I'm restricting myself to the glassy manifold. Basically, I'm assuming that when my temperature becomes smaller than the energy required to excite this mode, then I just have to work with whatever is left. So, yeah. Maybe there is a small probability, exponentially small probability that you can, basically, the probability will be exponential to the minus energy gap of this excitation divided by temperature. So it's e to the minus the energy for this excitation divided by T. So that's the probability that you will be generating. Yeah, so we are going to ignore that. So, yeah. Okay. So the point is that, so for the remaining mode, right? So you got rid of this mode. You also get rid of the T1 plus mode for the A tetrahedron. The remaining mode are all there. And they can be nicely summarized like this if you define a rank 2 electric field. So here, this is a symmetric piece of the rank 2 electric field. It's written in terms of normal coordinate of all the elusive representation. Right? These are the collective mode variable. And you just arrange it in a 3x3 matrix form. So this is symmetric part. And there's a part that gives you the diagonal piece. It gives a finite trace. And this is an anti-symmetric part that only comes from T2 mode. Here is the A2 mode. This is just irreducible label. Sorry, I just couldn't find the better way to write down a label, but that's basically what it is. Okay. So details are not important, but point is that this constraint becomes a Gauss law for rank 2 electric field. That's the point. Right? So we generate a constraint. That constraint is precisely the Gauss law for the rank 2 electric field. That is the point. Okay. So, okay, what's the consequence of this? So then you can make a further simplification if you assume that this additional mode or the mass for additional mode is actually bigger than the mass for E mode and T1 minus mode. So then I can just get rid of all these guys in the same spirit. If you do so, then the remaining electric field is just, you're just left with the symmetric piece. All the anti-symmetric part and the traceable part, they are all gone. Okay. So then you see that the Hamiltonian can be written nicely like E square form with the Gauss law constraint. And so this is precisely the rank 2 vector charge gauge. So this is mapping from that classical spin model to rank 2 gauge theory. That's basically the point. Okay, is that clear? Okay, yeah. So it's nice, right? It's so still, but I emphasize this is still a classical model. It's not a quantum model. Question is, can you make a quantum model out of this? Right? That's the question. Oh, by the way, it looks arbitrary, but by making some useful choices of exchange interaction, I can easily go to this regime. So realizing this, it's very natural. Okay, now you want to think about a quantum theory. Then you immediately realize that it becomes very complicated. The reason for that is these collective coordinates are really spin variable. Remember? So classically they all commute, but quantum mechanically they don't commute. So your electric field variable, even though it's looking nice in the classical theory, they're all non-commuting field. It's a spin, so they don't commute. So immediately it becomes an intractable problem. Like it becomes a non-commutative quantum field theory, and we don't understand this very well. Okay, so we have to find a different way. So we find that one can actually look at a different limit of the classical model. So I think suppressing all the details, we can choose E mode and A2 mode. I will tell you why I'm choosing this particular mode. So if you choose a parameter set in such a way that these two guys are the low energy mode, okay, then what actually happens is that we end up with symmetric and diagonal and trace 4 model. So I remove all this mode, off diagonal mode. I only keep E mode. These are the E mode, right? And I keep A2 mode. All other mode I throw away, assuming that the mass is too large. Okay. So if you only keep this, it's a diagonal piece that gives a symmetric part. But this guy will give you finite trace. Okay. The previous model was symmetric and traceless. Okay. So this model is slightly different, but still symmetric, diagonal, trace 4 is still a rank 2 theory. Okay. Now, so what actually happens? Oh, by the way, yeah, you can choose some parameters to get there. So but if you do so, then the sum of these two, I can define a new electric field, rank 2 electric field. Then they satisfy Gauss law constraint. So at this level, basically the same kind of physics arise. I have a rank 2 tensor here, electric field, and they satisfy Gauss law. Okay. Now the point is that this theory is much easier to solve quantum mechanically. I'll tell you why. So you look at the Hamiltonian. I have 2 mode, E mode and A2 mode. Right, E mode and A2 mode. So then, since I only have a diagonal piece in the symmetric part, what actually happens is that only like XX, YY, ZZ component are finite. So it's like the combination of this becomes electric field square in the X direction, Y direction, G direction. Only those elements are finite. I can define a vector electric field in the sense that XYZ becomes the XYZ component is vector. So it becomes like this. It's very simple with the same mass scale. I tune the mass of this mode to be the same. I can do that by changing some microscopic parameters. Then there's some perturbation from the B sub lattice. I should not forget that. So the point is, this, as I explained to you before, this electric field is really the spin collective mode. These are spin variable, right? So they satisfy usual spin commutation relation, right? So these are spinor variable, spin commutation relation. And if you define a vector like this, then they really act like a spin. Okay. So in fact, if you choose a z component and the electric field square as the commuting operator, then this is just like a SQ and SZ operator that we are familiar with in quantum mechanics. So you can almost regard this as S square. You can regard this as SZ operator, so that you can label quantum state using those quantum numbers like S and SZ. Right? So nothing abnormal here or strange. But what we should not forget though is that these relations are the same as the usual spin, but there's a constraint, right? Gauss law constraint. And that makes all the physics interesting. Okay. Now for each tetrahedron, one can show that if you have only 4 sides, then you can solve this problem exactly. The ground state is 5-fold degenerate, and the corresponding eigenvalue is just -2, -1, 0, 1, 2. Because if I can spin 2 state, it's the ground state. If you place a model like this on the single tetrahedron. Now I have to decorate the entire lattice using those states, right? And then also I have to make sure that only the ones that satisfy this Gauss law constraint survives. But nonetheless, there's so many states, so you end up with a massive degeneracy. The number of degenerate states is again exponential. Okay. Okay, I didn't solve the problem yet. Now, if you relax the Gauss law constraint, so you create electric charges here. What I mean by electric charge is the configuration of spin variable that violate the constraint, right? That's the free charges. So that's what I call electric charges. So using those electric field variables that I define for each eighth tetrahedron, it turns out the charges are actually located at the B tetrahedron site. Okay, B tetrahedron site. And you can define a charge like this. And again, those charge variables are really spin variable. So they also satisfy SU2 commutation relation. And they also satisfy since those are essentially spin variable, they satisfy usual commutation relation like this. Also, the raising and lowering operators can change the charges at the B sub lattice site. Okay. Okay. Yeah. So you can work out all this. It's just very simple quantum mechanics problem. There's nothing actually complicated at this point. It's just a SU2 commutation algebra. But what is crucial is with all these parameters, with all this variable, we should not forget there's a Hamiltonian for the B sub lattice. We are going to treat this as a perturbation. So this is a much weaker interaction. Okay. Now, since each spin on the B sub lattice also belongs to A sub lattice again, I can rewrite this variable only in terms of collective mode of the A sub lattice, degrees of freedom. So it obviously it becomes very complicated, but nonetheless you can write it. So for example, there's raising and lowering operators between 2 nearby A tetrahedrons. So you use the raising operator here, you use the lowering operator here, and they always come together, for example. Okay. So and that is quantum fluctuation. Yeah. The point is that this represents the quantum fluctuation. Just like the analogy to quantum spin ice problem, remember? This E plus E minus really gives you the fluctuation of a spin variable. So just to see operationally what it does. So again, remember this green dots A tetrahedron location. This is the location of B tetrahedron. This is the top view for that FCC lattice or the pyrochlore lattice. If you apply a raging operator here, one can show that the immediately generates this quadrupolar-like charges at the nearby p tetrahedron site. It generates plus, minus, plus, minus. So in terms of spin computation, it looks like this. This is the A sub lattice location. This, if you apply a raging operator in one of the lattice, one of the A tetrahedron site, then in the B tetrahedron site, you generate a defects. And those are spin defects, and those are upspin, downspin. You generate 4 of those guys. And now if you apply E minus at the nearby A sub lattice site, then you create again plus minus minus plus configuration. Then in the center plaqué, these 2 charges cancel. So you keep doing this. Remember, this is the perturbation or quantum fluctuation from B tetrahedron. You keep doing this, you again cancel charge in the bulk. Charges are pushed to the boundary. You keep doing that. Then notice that you create a boundary charges like this, but there's a bulk. In the bulk, there's no charges at all. You cancel all the charges in the bulk. You push out all of your charges to the boundary. Right? Boundary. Okay, you keep doing this, and then if you apply a periodic boundary condition here, then you can show that all of the charges can be canceled if you wrap them around the torus. So what that means is that after doing all these processes, I go back to another ground state. Remember that originally there are many, many ground states. I just go to one of the ground states, meaning that I start from one member of the ground state. I do all this perturbation, and finally, when this membrane kind of stuff expands and annihilate, I go to another ground state of the same ground state manifold. Okay, so we can keep doing this and generate all the degenerate ground state. And if you're familiar with the quantum Hall state, then this is very similar to like moving quasi-particle, create quasi-particle and anti-quasi-particle. You wrap them around the system and you annihilate, then you go to another ground state. It's very similar. It's very similar. Okay, so now what about the ground state degeneracy? This is not an exactly solvable model, right? This is a semi-realistic model. We don't, there's no exact solution, right? I was presenting some low energy effective lattice theory, but it's not exactly solvable. So we don't have an analytical formula for the ground state degeneracy. So we counted number of degenerate ground state by computer, brute force counting, just time consuming. And we didn't know whether the ground state degeneracy depends on volume or perimeter. So we tried both. So here, an example of geometry here. Remember that those green dots are 8 tetrahedron. So each dot is tetrahedron. So when I say Lx, Ly, Lz is 1 on 1, what that means is that I'm talking about this actually quite a big block like that. So there are many tetrahedron inside. So for this configuration, for example, this volume will be 1 in this unit, perimeter will be 3. If you count all the ground states, it's 85. There are 85 degenerate ground states. You increase the volume and perimeter, and we are looking at different kinds of geometry here. Here I'm increasing only one of the length, and I'm changing the size like this. So you see, sometimes you have an extremely large degeneracy. Also, ground state degeneracy is different for the same volume of perimeter. So same volume, ground state degeneracy is very different. Same perimeter, they're also very different. And if you fix the perimeter, and then larger volume gives you a smaller ground state degeneracy. That's very strange, isn't it? If you fix the volume, then larger parameter gives a larger ground state degeneracy. So that you can play this game. We couldn't find the analytical formula. I think that I need help from mathematician. I couldn't do it, but we found a pattern. So if you increase the lattice size only along only one of the direction, okay, so then ground state degeneracy monotonically increases with the system size. But in all other cases, it does not monotonically increase either volume or perimeter. Ground state degeneracy larger for larger parameters for a given volume. This we can understand because it turns out that the number of times that the membrane operators that I was creating, the membrane-like object, the number of those operators depends on the number of planes. And for FCC lattice, it turns out that there are 2 Li number of planes in each direction. So the total number of planes is actually scarce like perimeter like this. So that's the reason why larger parameter gives you larger ground state degeneracy, because I was using this membrane operators to generate another ground state, remember? So if I have more of those, I can create more ground state, degenerate ground state. Now, ground state degeneracy is smaller for larger volume for a given parameter. This we can understand too, because it turns out number of constraint increases the volume. So you have more and more constraint. Because of that, degeneracy actually becomes smaller and smaller. Okay, so this much we know, but we don't have an exact formula. But clearly, so I'm gonna maybe, well, okay. So another issue is I only told you about the electric field. You can ask me like, what are magnetic field? Where is the magnetic field, right? Because if it's a true quantum electrodynamics, there should be a magnetic field. The question is quantum fluctuation, can quantum book generate also magnetic field in the bulk? And the answer is that in finite order perturbation theory, in this particular case, it turns out it's not actually generated. In fact, what actually happens is that we can estimate the coefficient of the B squared term. So it looks like this. T is the coefficient of the perturbation, and this is the mass scale of the mode that I was getting rid of. Remember, I got rid of this heavy mode. So one can show that coefficient of B squared term scales like this. The point is that the thermodynamic limit is 1 over mu goes to 0. So in the end, what actually happens is that the speed of light becomes 0 in the thermodynamic limit. So for the finite lattice, speed of light is finite. But when the system size becomes larger and larger, the photon becomes slower and slower. That's what this lattice model tells me. Because of that, basically it takes a long time to tunnel between different ground states, because I have to use this photon to go from one ground state to the other. It just takes forever for thermodynamic light system. So in a way, you can say that photons are basically localized. So I think I use all of my time here. So I just say we have nice, more semi-realistic two-spin exchange model on the breathing pyrochlore lattice. That gives you something like a fracton ground state. For example, all these charge excitations can only move as a cluster at the edge of the membrane-like object. So they cannot move separately. And this sub-extensive ground state degeneracy depends on lattice geometry explicitly. And in this particular model, photons are localized. But we believe this is probably the first realistic model for the fractonic quantum ground state. So that's all. Okay, thank you very much.
Thank you very much, Yong-Baek, for this very interesting and nice talk. It's now open for questions. Yeah, I just add one question first. So you introduced this this material somewhere at the second part of the talk. So what are the consequences for the material after all this understanding of fractonic excitation?
Yeah, so the first thing we should see is some kind of very slow spin dynamics, right? Because if you have this fractonic ground state, then if you start from some one ground state, then since there are so many degenerate ground states, in principle, you should be able to go from one ground to the other. You should some quantum dynamics that connects one degenerate ground state to the other.
But I mean, in terms of, I don't know, material properties of physics, what would be the?
Yeah, so actually I don't know. So we don't have a specific prediction for this. Actually, this is something that I have been working with my postdoctoral fellow. So for example, unfortunately, for example, in this case, photons are localized. If the photons were not localized, then it's gonna give us like T cube type. Actually, for rank 2 theory, it turns out the photon dispersion is k squared. So the energy goes like k squared. So then you have some different power of heat capacity. But unfortunately, the coefficient of that heat capacity term basically goes to 0 in the thermodynamic level. So that's why it's very hard to make a prediction for that. Yeah.
Okay, questions?
I have a question. So if the photons are localized in the thermodynamic limit, then I guess these photonic bands will eventually touch the ground state degeneracy as it form like a perfect flat band limit. Then wouldn't it like destroy the topological order at any finite temperature?
Yeah. So actually, this is the description at 0 temperature, right? So yeah, I don't know. I think that's a good question. Whether this page is stable at finite temperature. Yeah. So I haven't really thought about that.
Thank you.
Yeah. But I'm not sure whether localized photon will immediately destabilize, the ground state.
Okay, more questions? Zoom people also, please feel free to ask questions.
I have a very simple question. So
Yeah.
in case, so in the introduction, as you mentioned that in case of band topology or the topological system, we have generally a bulk boundary correspondence, right?
Mm-hmm.
Bulk topological
Right.
variant gives the. So here also in long range entangled phases, does that condition also holds?
It's a different kind of bulk boundary condition, bulk boundary correspondence. So it depends on the phase. Sometimes, for example, boundary doesn't have to be gapless. The long range entangled phases, right? For the symmetric protected phases, boundary stays most of the time gapless.
Yes.
That's related to the bulk topology. For long range entangled state, it doesn't have to be the case. So for example, you can have a quantum spin liquid state, and the boundary can be boring. Then there will not be any interesting excitations. Of course, there are quantum spin liquid state that's more like a quantum Hall state. For example, in that case, there is a bulk boundary correspondence. So like if you remember what happens in quantum Hall state, depending on the Chern number in the bulk, you can have chiral edges there. So something like this can also happen for the chiral version of the quantum spin liquid in one-to-one correspondence to the quantum Hall state, but it doesn't have to be the case in general. So that's actually one of the main differences between the symmetric protective phases and the long range entangled state.
Thanks.
We have a question via Zoom. Alexei, please unmute yourself.
Yeah, thanks. This is more of a, perhaps I would like to clarify. So here the glassiness, when you were talking about glassiness, so because the photons are localized in the thermodynamic limit, so basically the glassiness arises not because you have barriers between the ground states, but because the matrix elements are suppressed. Just wanted to clarify that.
That's correct. Yeah. Basically, the matrix element is suppressed. So the point is that, so in some sense, photons actually can connect like from one ground state to the other, but the photon is very slow. So actually, that's also related to this quantum glassiness, right? So when you start from some initial ground state, it takes very long time to relax to another ground state. You just get stuck in one of those. In principle, there are many, many degenerate ground state, but something, force you to be in one of the ground state. It's very hard to get out of that, basically. It just takes, the matrix element is just very small, so it just takes a long time.
Okay, and the other question I have, essentially, am I right? So I would like basically to ask how generic is this construction? Because let's say, can I say that this model, essentially, you can get the rank 2 theory by fine-tuning rank 1 theory, by tuning some parameters such that you impose the dipole conservation.
That's correct, but the point is that it's not what I should say. It's not tuning. It's not tuning parameters to some particular single value. So there's a range of parameters where all these conditions are satisfied. Remember that I started with some microscopic spin model, and I can show that this condition is met in some reasonably large area in a parameter space.
Oh,
so
yeah. Oh, yeah. When I meant fine-tuning parameters, I also meant that there might be many, and a constraint could give you a manifold of solutions. That's fine. So I'm curious how generic this construction. If I cannot immediately think of other lattices, but do you think this breathing structure is essential, and you can come? I mean, there are other.
No, it's probably not, right? So here, roughly what I used, in fact, what was important is the fact that the dual lattice is a bipartite lattice. That's the structure I use. Basically, I'm using the constraint from one sublattice to impose, one sublattice. Basically, I'm using the degree of freedom in one of the sublattices to impose a constraint on the other sublattice. So I just use the bipartite structure. So in principle, I think that this can be applied to any bipartite lattice as long as dual lattice is bipartite lattice. I think that this can be applied. I don't think it's special to reading pyrochlore lattice.
Okay, thanks.
Okay, more questions? Zoom people? Real people?
Actually, I had some difficulty in understanding this non-monotonic behavior of the ground state degeneracy. So to me, it is very unnatural because adding just more degree of freedom, larger system would just increase the ground state degeneracy. But you said that somehow that will increase the constraint.
That's right. So there's a competition.
So
when you increase the system size, the number of constraints increases the volume. The number of sort of operators that would essentially count the number of grounds that that actually increases. So when perimeter increases, in principle the number of degenerate grounds that increases, but when you increase the system size, volume also increases. Then the number of constraints also increases. So if you increase the number of constraints, the number of degenerate grounds that becomes smaller. So there's a competing effect. So that's why it's not a simple counting formula. It's it doesn't monotonically scale with either perimeter or volume because number of constraints increases the volume. Number of operators that can in principle count the number of degenerate that also increases. So again, if you have a more constraint, the number of grounds decreases. So there are two competing effects when you increase the system size. So that's why it's not easy. We couldn't find an analytical formula. So just took a long time to count all of them, but that's the best we could do. It's not exactly solvable model. Again, I emphasize. So we don't know a lot of things about this model.
Thank you.
Okay, more questions? Alexei, do you have more questions or you forgot to lower your hand?
Now I have a further question, although this one is a generic one. I'm curious if would anything interesting come out if you increase the number of conservation laws? So if you go to rank 3 theory.
Yeah, so then your motion of quasi-particles are more and more restricted. So you can imagine, like, you conserve a total charge, the dipole charge. You can also require that quadrupolar charge is conserved. Then you can only create like octopolar kind of charge configuration. So the motions of these charges are more restricted. You keep doing that. So you can define like some kind of multiple constraint. Yeah. So it's just that the more and more constraint you apply, you're restricting the types of excitation you can create. So they should all appear as a cluster state, obviously, right? Again, you cannot create a charges individually anymore, right? When you impose this. So the number of cluster charges that you should have to increase generally increases, right? When you impose more and more constraints.
And what will happen, say, if you, yes. So, and what will happen if you take rank 1, let's say, if you consider a boundary between, say, rank 1 and rank 2 theories?
Sorry, you start from rank 1 theory?
I mean, what happens if you, what happens if you consider a boundary between rank 1 and rank 2 theories?
The boundary.
Yes, I'm thinking what. Yeah, I'm thinking if these constraints are now not applied homogeneously in space, but in one region of space you require that only charges are conserved, and in other region, say in the other half space, you allow you require that both charges and monopoles are, sorry, not monopoles, dipoles are preserved.
Yeah. So yeah, I didn't think about that. That's an interesting thought. I guess you can have some, I suppose, so some quasi-particles basically cannot tunnel from one part to the other, right? Because you'll be violating the constraint on the other side. So you can only move along the boundary, I suppose, right? Some particles can only move along the boundaries, parallel to the boundary, but not perpendicular to the boundary. So you can move them at the interface surface, but not perpendicular, not in a perpendicular direction. So that's what I would expect. Yeah.
Okay. Thank you.
Okay. Are there any more important questions? If not, then maybe we should stop and thank Yong-Baek Kim very much again. Thank you.
Thank you very much.
And just as a further information, so Yong-Baek will leave tonight back to Kias, Seoul, where he will stay until I think the end of next week. So if anyone wants to reach out in our time to him, then you still have time until the end of next week. Okay, thank you.
Thank you very much.